Okay, good afternoon, everybody. We're almost towards the end of Summit, but we do have one very special presentation still to go. Michael here from a global pharma is here to talk about estimation. And just before I hand it over to Michael, a couple things about himself. He's visited 31 countries, which I, before the session, wrote down all the countries I visited, and I came up with 14, so you win. Some highlights were he went to the Instrument Museum at Habsburg Palace in Vienna, Toyota Museum in Nagoya, Japan, based on the pronunciations. I've been to none of these. And he saw a sunset from the beach at Applecross in the Scottish Hebrides. Again, never been there, so put that on the to-do list. Okay, take it away, Michael.
Great places to be. Thank you for coming out. I wanted to start with asking how many people here feel like they have like a good handle on estimation? Okay, how many people here can actually raise their hands above their heads, right, going out? Because there's science that proves if you raise your hands above your head, you feel happier. So you should go ahead and do that. And so how many people here feel like they do a good job at delivering software, right? They're like, you're in there, right? And so part of what I want to try to do is to close this gap, because I think that a lot of what estimation is in practice is pro forma estimates, where you set a target and then you're held to this target. And really the kind of work you do as, when you build software, you start with something that's very uncertain, you end up with something that's certain. So you reduce uncertainty. That's what you're good at, if you're good at software engineering. Estimation is the same thing, right? So I want to try to connect those dots to realize a lot of the talents you already have in software engineering, whatever role you're on, are actually applicable to estimation if we kind of get rid of some of the diseases of how we think about estimation and think of estimation as uncertainty reduction. So I started out building software over 30 years ago, and one of my earlier gigs was with an electrical contractor. And this was when my mom and pop days, when I was like just figuring things out. And so he taught me how he did things on paper in electrical estimation, and I modeled it in a Quattro Pro spreadsheet, and I learned a lot about estimation in the process, and I've thought about it a lot ever since. And there was a thing that happened at the time there was this news story. It really made a big impression on me, and it was the bankruptcy of the largest construction firm in Vermont, where I was. And I knew some of these guys. It was a family business. They went up in smoke over a single bid. And it was the Northfield Elementary School re-roofing project. And it was just another re-roofing thing. It was a lot like all these other projects they did. And the estimator, he was an expert. He walked up on the roof. He walked it through before writing up his bid. But what he missed was just how many times that roof had been resurfaced over the years with layers of tar and gravel. Looked all the same. Right? And in the fixed bid was the cost of removing all that stuff, which turned out to be millions of dollars in removal costs. So it's the roofer's version of technical debt that they got into. And all he had to do was core drill the roof, and he would have known what he was bidding on. But instead, he just compared it to all of the other projects they had successfully done before, and that had been a reliable technique up until the project that brought their company down. And ever since, whenever I've been asked for an estimate, which has been like all the time, like every day, when I go back to work Monday, I'll be asked for another one. I can't help but think of that guy standing up on the roof who was about to bring his company down, right? And it brings to mind this Mark Twain line, which is essentially about when you're expressing certainty about something that you really don't have business to be certain about, which is a lot of what we do when we're facing software stories, right? We don't really know exactly what we're looking at, but we still offer up some number, right? Because we have to. We're expected to, right? And so I've been thinking about this for a long time, and it was really only recently that I learned some stuff about how to leverage uncertainty in the estimation process. So that's really the root of what I want to share with you here today. And so, as project managers and developers, we're routinely asked to navigate ambiguity, such as being asked to produce an estimate against hazy business objectives or obviously making like commitments against obviously changing scope. But as important as estimation is to setting stakeholder expectations, when I went in to actually study through as much literature as I could find, really I found that there's not that much material about really actually what estimation is. There's a lot about how to manage the estimation through the business process. There's stuff about story points and planning poker, but there's not very much about what estimation actually is or how to do it. And so typically when we're asked for an estimate, what do? Right? We bring together our domain experts. We ask them to size things up. Here's our story. And we have them make a stab at what they think is going to be the most likely outcome. And they're going to express it as a discrete value. And a discrete value, I mean, they're going to say, that's 4 hours, that's going to be 2 days, that's going to be a week, that's going to be 3 weeks. And to understand really the implications of discrete value estimates, you have to think about how assumptions are handled. When we expect that after the work is done, that the actual cost is going to be different than what the estimate is, because we know there's going to be factors that we don't know about, we can't control the outcome. So when we estimate, we substitute these unknowns, or at the beginning we don't know, we substitute the unknowns with assumptions about what they might turn out to be. So for example, if we've got some story about some third-party API, we've done a bunch of APIs we can compare it to, we know that there's risk, we don't know where it's going to be. Supposedly it's a RESTful API, I don't know. And so we provide a discrete value estimate, but we increase the size of it to accommodate this sense of risk that we have, right? And that increase in size becomes an implicit part of that discrete value estimate. And so when we inflate our estimate to accommodate risk and uncertainty, it becomes harder to know what part is how long we think it'll take, and what part represents that contingency that we put in for various assumptions, which may or may not play out, because we just have that one number. It's like 2 weeks, right? Once you're halfway in, where's that assumption as you get more knowledge? So instead of lumping assumptions in with effort estimates, we can make it easier to keep track of risk and uncertainty by expressing our estimates as a range that's most likely to contain the eventual value. And so using range estimates gives us a much more powerful way to express uncertainty than bundling our assumptions in, because you don't have to commit to anything that you're uncertain of, right? The range and the probability reflect your uncertainty. If you don't have a clue, then you just have to widen the range until it reflects what you do know. And I know that your boss wouldn't accept that, right? We'll talk about that. So in contrast to tarballing assumptions into a discrete estimate, a range makes your uncertainty evident, leaving it exposed for ongoing, even iterative evaluation. And if you're afraid to have the truth of your uncertainty exposed, that's kind of a different problem. But we want it exposed. We need it exposed in order to continue to work on it. So the essence of estimation is an iterative process of reducing your uncertainty through observations. Now, reducing uncertainty is a question of first really clearly identifying what it is that you're uncertain about. So that it's primarily decomposition. So you break down the question, classify, compare, discriminate, and so on, until you can really reason about the components independently. So until you can get to that point, you don't really have something to work with. Decomposition is the fundamental part, and that's a whole process in itself. But then once you have something that you can reason about independently, then you ask, why things matter. What about your uncertainty really matters? What are the possible outcomes? What are the decisions that would be affected by additional information? So if you're looking at this third-party API, we still don't really know exactly what it is. We know that we have to code error handling, and we have an uncertainty about it because we know that if it's a clean API, it's going to give us back 400 errors or it's going to give us 400 codes for all the errors, and it's going to be trivial to code it. But if you stumble into it and you find out they've got some errors come back as 400 and some are coming back as 200s with an embedded error message, right? And then you've got all this extra work that you have to do. You don't know until you get in there, and so this is the stuff you have to sort out. So range estimation doesn't really take any more time at this point, right? stating things different. You're expressing things differently. If range estimation results in like a greater comprehension of your uncertainty and you end up spending more time in the estimation process, then we'll take that really as a good thing because you should be able to get paid back in a cleaner execution when you go into work. If the actual uncertainty results in a range that's too wide for comfort, then you have to figure out what questions, if you had the answers, would reduce uncertainty. And so, I'm sorry, I'm just going here. So there's this Bell Labs researcher from 1948 who wrote a paper called The Mathematical Theory of Communications. His name was Claude Shannon. And he postulated that information is the amount of uncertainty reduction in a signal, right? And so this is really the foundation of the information theory that we're talking about and when we talk about estimation as uncertainty reduction. So Shannon's conception of information as uncertainty reduction was fundamental to the emergence of information theory, signal processing, the development of integrated circuits, the zip compression algorithm, MPEG, MP3. Shannon is really a towering figure in everything that brought us together for what we're here today. And it's an important part of what I want to share with you in terms of how to rethink what estimation really is all about. Thinking of information as uncertainty reduction opens us up to a world of measurement where uncertain values are now first-class citizens. Instead of being afraid of things that we don't know how to measure, we can look at them more closely. And we can more easily take into consideration intangibles that we once dismissed as not subject to measurement. So Shannon referred to the reduction of uncertainty as the removal of entropy from the thing being measured relative to its prior state. So it's an iterative process of uncertainty reduction that increases the fidelity of the signal. And that's what an estimate is you can think of it as a signal. You're trying to get to a cleaner signal. So the definition of entropy is that it's the average amount of information conveyed in an event when considering all of the possible outcomes. So when you do a 2 coin toss, then the information entropy is the base 2 logarithm of the number of possible outcomes, which is 2 coins is 4 possible outcomes is 2 bits of entropy. Now think of it in terms of a software story that you're looking at. The entropy is what you don't know about that story, right? So the basic idea of information theory is that the more one knows about something, the less new information that you're apt to get. That's the fidelity of the signal. The converse of that is what I'm calling estimation as uncertainty reduction, is that the less you know about something, then the easier it is to obtain new information. This is often what we overlook. When we're looking at something we have no idea, that's actually easy to obtain something that'll help us know something more about it, rather than staring into the blindness of it. So here's a brief example is, so if you had to know out of everybody that came to this summit, what's the average amount of time people spend in meetings during an average work week in order to build your story, how many people would you have to survey to get that piece of information? 2/3 of the people, all of them, half of them? What if we walked out in the hallway and we asked 5 people at random? How much would that additional information actually contribute to reducing the entropy of the question? Right, 5 people at random out of everybody that's here. All right. And the fact is that there would be a greater than 90% probability that the actual median of the time of everybody falls in the range that's bounded by the upper and lower response of a random sample of 5. And that's the math of the normal distribution. You can go through that. The main point is that when your prior state of uncertainty is really great, such as is in this kind of example and such as is often in software stories, then a surprisingly small effort can yield useful outcome in reducing uncertainty. And our measurement doesn't have to vanquish uncertainty to be valuable. It's another part that we miss. We're thinking about a definite number, right? We're saying, how long is this going to take? And all we want to do is to get to something that we can start with and continue to chip away and reduce that uncertainty. That's what you do in software engineering anyway. We just want to give you the skills to be able to do that more up front, right? We didn't actually learn the actual average meeting time from a sample of 5. All we learned was a range in which the actual median is likely to fall in the middle in there. So now when we quantify our uncertainty by expressing our estimate as a range, we're saying that we're confident that the actual value falls somewhere in that bucket. And so it's reasonable to wonder, what do we mean by confident, right? And so we could say, with really great confidence, I've got a task. It can be done between a day and a year. And that wouldn't really help anyone, right? But it would be, definitely it's going to get done in there, right? So to be useful, your range has to be in striking distance of reality. And again, there's math that defines that. It's again, normal distribution. To be useful, your range has to be within, like in your 90% confidence. And that means that your actual estimate has to fall above or below your, the actual result has to fall above or below your estimate some of the time in order for your estimates to be credible at all. You have to be wrong some of the time. If you're always right, then you're just underestimating. And so if your estimates are right 9 out of 10 times, then we'll call you a properly calibrated estimator. Okay? And that's a thing, right? So mostly we think about calibration, we're thinking about tools. And I spent an entire year in 2001, that's all I did was for an airline. We did tool calibration and software, right? One end to the other. And it was because there was this Alaska Air 83 that went down in the Pacific Ocean that year. And the FAA was over all the airlines it was all about tool calibration. Because the plane went out of the hangar serviced for work, and based upon the screw jack and the rudder having been measured by a tool that said it was good for service, but the tool wasn't properly calibrated, right? And it was a fatal crash. So calibration is a procedure where you measure against a known quantity, so that when applied against something that's unknown, that you can have some confidence in the observation. The definition of calibration. So what's that mean for people, for humans, calibration? Because we can't measure your calibration in terms of estimation with weights, right? Or with a ruler, right? Now, bookies and actuarials, in order for them to stay in business, they're actually calibrated professionals. So there is such a thing, right? For the rest of us, when we just have, we're relying on our expert judgment, then we have swings of overconfidence and underconfidence, especially overconfidence, where the actual value is underestimated, right? And so estimation calibration for people is where you put us up against a series of exercises to raise the individual's awareness of how to make their statement of probability more accurately correspond with their actual uncertainty about arbitrary questions. And so arbitrary questions, trivia questions, can be used to gauge your sense of underconfidence and overconfidence, so you can begin to recognize that. And I can point you at the end to a company that's in the business of calibrating teams. You can go to them and they'll work you through the exercise. So we have a concept of estimation as uncertainty reduction. When we go to apply it, then we need to apply it in terms of measuring things. And so we go to another paper. Around the same time as Claude Shannon, there was a psychologist named Stanley Smith Stevens, who published a paper called On the Theory of Scales and Measurements, and he gave us a taxonomy of measurements. And you're familiar with some of them. Nominal, ordinal, and rational scales are in every software language, but interval scales is also included in that. And you use interval scales every day yourself, you're just not aware of them. Rational scales are these ordered sets: addition, subtraction, multiplication, division, time and money are rational scales. You can roll up a group of time estimates to a single value. You can multiply them by 2 and know that that value is twice as long. A rational scale is the only place you can do that. And we use all these other measurements as well. Interval scales are a lot like rationals, except they have no fixed 0. And so Fahrenheit and centigrade are interval scales, and so it has an arbitrary point on there. And they're used extensively in behavioral psychology and other areas. IQ is an interval scale. Story points is an interval scale. So if you use story points, you're on an interval scale. And if you don't know how an interval scale works, then you're flying blind on story points. Ordinal scales are ordered sets, but you don't know how much more one value is than another. So Mohs scale of mineral hardness, it tells you that one rock's harder than another, but not by how much. So you can say that granite's harder than sandstone, but the scale doesn't tell you how much harder one thing is than another. And we use ordinal scales all the time in estimation. Look at the 5-star rating system, right? Is watching 5 1-star movies the same amount of fun as watching 1 5-star movie? Right? There's no roll-ups in ordinals, but people do it all the time, right? And what is it? It's like mathematically nonsensical. And so when you see roll-ups in ordinals, then think twice. T-shirt sizes is an ordinal scale, but it's really frequently conflated with a rational scale because this intense desire to add numbers up. And so when you put time values on T-shirt sizes so that you can roll them up, then you're kind of mixing 2 different scales to do one thing. And sometimes it'll work, but other times all you're doing really is increasing the uncertainty rather than reducing it. The Alistair Cockburn proposed an ordinal scale specifically to correct for this common problem. And he names instead of T-shirt sizes, we use cherry pit, peach cobbler, Mustang, and Brontosaurus. And it's perfect for backlog refinement. Everybody gets cherry pit. Nobody's trying to figure out how many peach cobblers to put in a Mustang. We don't know whether a Mustang's a car or horse, doesn't matter. And a Brontosaurus is any story that's too big to go into work, right? We don't care how much bigger one Brontosaurus is than another, right? So it gets over it's kind of whimsical, but it prevents people from like conflating rational. Anybody that wants to do that, because you should just be doing an ordinal scale thing at this point. Keep it in ordinal, force that in ordinal. Because conflating it with the rational is not going to help you at this point. You need to go through a different process that comes later. Nominal scales are, you also use them all the time, but everybody discounts them when it comes to estimation. Everybody wants to get to numbers that they can add up, right? Hours, days, money, right? But nominal scales are unordered sets of attributes, so essentially you're testing set membership, so you use them in programming all the time. Having no quantitative value, there's no roll-up. There's nothing to roll up in a nominal, because each attribute is either true or false. So there's as many nominal scales as there are things in the universe, or attributes in the universe. You really have a lot to choose from. But one that you're probably familiar with is invest from Scrum, right? To get a story out of the backlog into work, the story should be independent, negotiable, valuable, estimable, small, and testable, right? If it passes all those attributes, then it's ready to go into work. That's a nominal scale estimate. It is an estimate. This is estimation when you do that, right? Now, those are binaries, so they can either be true or false, but really our certainty is rarely binary about these things. And so you can really extend this nominal scale estimates by providing a confidence interval against the binary attributes. So you can express your confidence in a range from 50 to 100%. 50% is like flip a coin, right? You can't be any less uncertain about true or false. And so if you have, for example, if your team is all weighing in and saying, yes, we believe this story is independent enough to go into work, but our confidence level is like a little bit low, then it's a flag that you know that you have some uncertainty to keep an eye on. But if the confidence level is at 100% that this is a valuable story, then nobody has any uncertainty about it left. So it's a way to preserve the uncertainty as you go into work, so you can continue to iterate on this. So we have the concept of estimation as uncertainty reduction. If nothing else, we've drilled down that you need to learn and pay attention to how different measurement scales work and really take advantage of them, and not just simply resort to rational scale measurements, because you need all of those measurement tools in order to really fully grasp, get a handle on uncertainty. In this last part, I want to go through a series of exercises. So if you haven't done, is anybody doing range estimation at all? This is like a new thing. Hardly anybody I meet is doing range estimation. Almost the entire scientific world works in range estimation, right? And so this isn't something new and unique. It's kind of the software some industries have gotten into. We've got particular practices. I'm trying to bring you back into the whole scientific fold, right? So when you start doing range estimates, here's a series of things that can help you kind of kickstart your process, right? And so the first one, this is from Doug Hubbard's series, is the absurdity test, right? And this is a common thing. I get a story, I read it, my answer is, I have no idea, right? More often than not. This is very common, right? And so the absurdity test is just start with a day to a year, and then just keep bringing your range down until you can get your range to the first range that doesn't feel absurd. And so you've gone from, I don't have any idea, to something where you can say, I guess this, yeah? It may, 1 to 3 weeks. It doesn't feel absurd, right? Once I get past 3 weeks, it feels absurd. It's valuable tool, right? It's simple, it's valuable, anybody can do it. Imagine you're wrong, right? So you've gone through, you've done some analysis, you've come down and you said, this is a 5 to 7 day story, right, going in. So before you lay that story down, lay that estimate down, you step back and imagine that you're wrong, right? So you go, okay, 5 to 7 days, it comes in, imagine it comes in at 10 days. What is it that you missed? What could go wrong? What are questions that you could ask now before you get started that would help you validate the range that you go in? So it's a way to kind of, force and reevaluate the question when you're at the point of committing. Testing for midpoint anchoring. Again, it's one that you can do at any point, but especially you're at the point of commitment, right? So you're in, technical backlog meeting. You're laying down your estimate. You're trying to convince yourself that it's the right estimate. Now, typically, when you start doing range estimates, what you'll do this midpoint anchoring. You'll say, I think this is like a 2-day story, so I'm going to say 1 to 3 days, right? You just add on either side of your discrete estimate, right? It's normal. It introduces the risk of midpoint anchoring, and that's a well-documented psychological effect that once a number is stated, it's harder to move off of it, even in the face of new information. And so a way to try to force you away from that place that you're in is to examine the upper bound independently. Just look at that 3 days and say, what's the likelihood, do I really think that I have a 95% chance that it's going to fall below this by 3 days? And then evaluate the lower bound independently. It's just a way to work through the mental exercise, the upper and lower bound independently. The one that I find probably the most useful, I'm not sure what happened to the text there, but equivalent bet, okay? This is a great one. So imagine a carnival wheel, right? So it's got 10% of the carnival wheels in red and 90% of it is in green. And what we're going to do is we're going to test your confidence in your stated range against a spin of the wheel. And you can do this in your head right before you're committing to your estimate, right? So the test is we're going to give you $1,000. And there's a lot of evidence that shows that betting with fake imaginary money has the same emotional effect as real money. So it's pretty effective. We're going to give you $1,000 if the real answer, the work actually comes in your range, or you can choose to take $1,000 by spinning the wheel, right? So which do you choose? Now, I'll tell you, almost everybody that starts off doing range estimates, when it comes to the equivalent bet, they're going to take the wheel, and that indicates that your expressed range isn't really your 90% confidence interval. We're almost always underestimating. It's not just in software, it's like a human characteristic. And so when we're thinking 1 to 3 days, it's actually, you want to get to where you feel ambivalent between spinning the wheel and your estimate. And that's kind of a way to prove that your estimate is your actual 90% confidence. You have to get away from this idea of your estimate proving your ninja worth by putting in a low estimate. Because what we want out of an estimate is your actual uncertainty, because that's the only way that we can actually proceed to getting the work done, right, is to actually identify uncertainty and then reduce it. So we're not interested in how fast you think you can get it done. We're interested in your expression of what you're most uncertain about in getting the thing done. Arbitrage is like an advanced team sport, but it gets at the idea of what we're trying to get at with a 90% confidence interval. So in this case, you could use a little software support in this. And this is where once you commit to your estimates, like the team members can buy and sell contracts against each other's estimate about whether their estimates are in range or not. And you should feel ambivalent about whether your team, like a currency exchange Forex trader, right? You should be ambivalent about whether people are buying or selling contracts if it's actually your 90% confidence interval, right? And everybody's buying, right? And they think that your estimate's wrong, then you're nervous about it. It's a sign, right? So we're trying to just get that sense of giving your own sense of what a 90% confidence interval really is. So here's where I kind of went off stock, because I wanted to simplify this, because to say the whole point of estimation is to support decisions, right? If an estimate doesn't help you resolve uncertainty about a decision that you have to make, then it doesn't have any value. And I realize that we're all in organizations where people are asking us for estimates where they don't actually have any value, and you still have to provide them. But you have to keep that in mind, that if an estimate doesn't provide, if it doesn't help resolve uncertainty, then there's actually no value there. When a pro forma estimate, you put it out as this is what I think it's what it's going to be, if that becomes a performance target that they pin on your back, it has a negative value. But there's really substantial value if the estimation process is understood as like a quantitatively expressed reduction of uncertainty based on observations, right? It's a scientific process. You're already doing it in your software engineering practice. You need to take your engineering skills and convert them into these kind of skills where you can flesh this kind of stuff out ahead. Now, I realize that that this is a really hard talk to take this information back to the workplace, because you have all of this other infrastructure around you about how estimates are used, and it doesn't answer all the questions. And so there's 3 areas that we need additional discussion that we don't have time for here. Story decomposition in its own right is there's few things more important to a software team than getting story decomposition right. And when people talk about no estimation, #no estimation, basically they're talking about if you get the story decomposition right, you don't have to estimate, which is true, but backwards, because getting story decomposition right is estimation, right? So they're confusing. It's a confusing conversation, but it is true that if you get decomposition right, then you're gonna do okay. No matter what else happens, you'll do okay. It's the first thing that you have to get right, because you can't do the other parts without it. Release planning, right? We talked here about effort estimation, right? And typically, people are adding in queue time in their estimates, but you can't ask the dev team to predict how long things are going to wait for test, wait for release, wait for pull request review, peer review, client review, any of that stuff. And you shouldn't try to be bundling that stuff in. We can estimate that stuff, and we can talk about that. It's a whole nother topic. But the estimating queue time is an estimation of the system that you're putting work through, not of the work. And then when we bundle together the kind of effort estimation that we're talking about here with an analysis of the system, we put those 2 pieces together, then we can actually get to reliable release management. That's what that's about, queue time. And then when you get to the part about, well, what about the money? That's where everybody wants to know how much money this stuff is going to cost. Monte Carlo simulations are a math that you can roll this kind of bottom-up, top-down project estimation into Monte Carlo simulations and manage the money of a rolling, agile software project in a meaningful way. Again, based on range estimation and uncertainty reduction. And again, that's another part all the way through. So I wish we could talk about all those things. This is a bibliography that I can leave up of a lot of the material that went into this. The Kanban book is one that I would highly recommend by David Anderson that's going to cover queue time more than anything. And Doug Hubbard's book, How to Measure Anything, Finding the Intangibles in Business, is that's the cornerstone of my talk. There's a lot more material there. It's not about software, it's about a lot of other things. They're the company that will actually give you calibration training. You can take your team, well, I mean, you can do it on the web, right? You can contract with them, they'll calibrate your team. It's a great exercise. So thank you very much for coming out. I think we have time for a few questions here.